Good afternoon. So we'll begin with module 3 right away. Start with implicit differentiation. And from the word itself, it's the opposite of explicit. And let me explain the difference between the two kinds of differentiation with this example. Let's find the derivative of y with respect to x if x and y are related by this equation. Now note that here y is not given explicitly in terms of x. So one way we can find y prime or the derivative of y with respect to x is to first solve for y in terms of x. That can be done. No, not always, but in this instance, we can easily get y in terms of x. So let's solve for y. And we can do that by factoring out y, giving us this equation. And we can get y by simply bringing this down. So we have y equals 1 all over x squared plus 1, which we can rewrite as x squared plus 1 to the negative 1, so that we can easily get its derivative by applying the chain rule for power functions. So getting y prime, we apply the power rule, bring down, subtract 1, differentiate the base. So we get this. And simplification gives us the derivative as negative of 2x all over x squared plus 1 quantity squared. So here we have gotten the derivative by explicit solving for y first, then differentiating after. However, there's another way of getting the derivative of y without resorting to solving for y first, especially if that cannot be done, as in many cases. But let me show by implicit differentiation how to get y prime. We start by directly differentiating the given relation or equation between x and y. So it's the given equation here, and we differentiate both left hand and right hand sides with respect to the independent variable, which in this case is x. So if we do that, we can apply the usual rules of differentiation. So for instance, for the left hand side, we can apply the sum rule. We can differentiate term by term. And then for the right hand side, the constant function rule, which states that the derivative of any constant is 0, giving us the following. Okay, derivative of the first term plus derivative of the second term equals 0. Now for the first term here, we can apply the product rule. If we do that, we'll get the following. It's the first function, x squared, times the derivative of the second function with respect to x, so that's just y prime, plus the second function, which is y, times the derivative of the first. So the derivative of x squared is 2x. And then we just change notation here from dy dx to y prime for a shorter hand notation. And then this gives us an equation relating y prime, x, and y. And we can solve for y prime here. And we can do that by isolating or transposing terms without y prime to the other side. So we will be transposing this one, giving us this equation, which we can solve for y prime by factoring out y prime, then dividing by the factor here. So giving us y prime equals negative 2xy all over x squared plus 1. Now note that this is already a derivative of y with respect to x, only that it is implicit in x and y, meaning the derivative, instead of being given directly in terms of x alone, the independent variable, the derivative now is in terms of both variables, x and y. So that if we know the values of x and y, we can substitute those values into the formula here to get the derivative there. However, we can show that the two answers are just the same by using this again, this one here. We can plug this expression for y in here to get this one. So replacing y by this, and then simplifying, we get the following: negative 2x all over x squared plus 1 squared, which is just the same as the previous answer. Okay? Now, as I have said, we cannot always do method 1. Only in actually the very simplest of equations can we do that. So usually we resort to implicit differentiation to get y prime, and that would be in terms of both x and y. So we call it implicit differentiation since the derivative is given in terms implicitly in terms of x and or y. Let's show that with another example here. So find y prime given the relation here between x and y. By the way, I call it relation since y is not necessarily a function now of x. If we try to sketch the graph of this equation, which I haven't shown here, actually by the vertical line test, it will fail to be a function. So we call this really a relation, or just an equation relating x and y. But still, we can get the derivative by implicit differentiation as follows. Now, what you do is simply apply the rules again, term by term differentiation. So let's start with the first term here. Applying the product rule again, first times derivative of the second, which is 2x, plus the second, which is x squared, times the derivative of the first, which is 3y squared. Don't forget y prime, and this is where students often get confused. You're differentiating y cubed, not x cubed with respect to x, so you have to apply the chain rule. In other words, after applying the basic rule, which is the power rule in this case, where you bring down 3 and subtract 1, you have to differentiate the base, remember, with respect to x. That is dy over dx, which is just y prime. So to omit y prime would give you a wrong equation here for the implicit differentiation. One wrong thing like that would cost you almost the whole problem. So that's the first term. Then we do also for the second term, we differentiate it, applying the chain rule, remember, for trigonometric functions. So constant, so that's just 2 times the derivative of sine y. How do you differentiate sine y? We know that the derivative of sine y is cosine y. And then since this is not x, but rather y, we have to multiply always by the derivative of y with respect to x. To omit y prime again would mean a wrong solution, and thus a wrong final answer afterwards. And then right hand side now, we differentiate with respect to x. So we need the product rule again. So first times the derivative of ln y, we know this to be y prime over y. Actually, we have stated it as a formula. The derivative of an ln can be obtained by getting the reciprocal, remember, of the expression inside multiplied by the derivative of the one inside. And then second term, which is ln y, times the derivative of the first with respect to x, and that is just 1, written here for the purpose of showing you what happened. So this gives us an equation allowing us to solve for y prime implicitly in terms of x and y. Now, how can we solve for y prime here? Well, first, we need to manipulate this equation so that no fractions appear. And then second, we must isolate y prime on one side. And to be able to do that, we have to transpose all terms containing y prime on just one side of the equation. But first, let me simplify this equation by multiplying by the LCD, which is y here, the only term, okay, in the denominator or in a denominator. So we multiply both sides by y first so that no fractions appear. So we have to do it term by term. So here we multiply by y, that becomes y to the fourth. Y squared becomes y cubed. And then here you have 2 times y. And then here y cancels out. So just x y prime. And then a y here. So no fractions appear in this line. And then collect all with y prime on one side. We have this equation. Of course, all other terms will be on the other side. Those without y prime. Then here, those with y prime. And the reason for doing so is that we can isolate y prime by factorization of y prime, which I will just show here. Although you can omit this step once you're familiar with the process. Factoring y prime will leave you with just the coefficients, okay, quote unquote, coefficients of y prime. And afterwards, you can just bring it down to get the expression for y prime. And we have y prime in terms of x and y found by implicit differentiation. So that's implicit differentiation in a gist, but I plan to move ahead with the other topics. At least you have an idea of uh, how to go about the process of differentiating implicitly. And don't worry, we will have exercises afterwards once we are through with all the topics. But at least you understand now how to get the derivative implicitly. So it's just practice that will make perfect for your understanding of differentiation. Any questions so far? So it's just all the rules you've learned in the previous module, except that you're now dealing with an equation instead of a function. So we apply this to getting the equations of lines tangent to curves. And when you say curves, they need not obey or what they call this, they need not satisfy the vertical line test. So you can have closed curves here, like circles, ellipses, and other shapes, as we shall see in this example here. So suppose you encounter a question like this where you're given, you see here, an equation, a relation, and it has a graph, but you don't have an idea of the graph. Don't worry, you don't need really the graph to solve this one, but I'll show you the graph anyway later on. And you are being asked to find tangent lines to certain points on the graph. Okay, I have omitted the additional question here where you should find the equations of the lines tangent to the graph of this equation at x equals 1. Just take note of that, at x equals 1. So you're not given the points of tangency yet directly. So the first thing you need to do or need to find are the points of tangency. So again, at x equals 1, that means you substitute x equals 1 so that you can get the corresponding y coordinates. Of course, if it's the y that's given, you have to solve for x. So if we substitute x equals 1 into the equation here, replacing each occurrence of x by 1, we get this. And this gives you an equation in y. And I won't be detailing out the process of solving for y here. It's your algebra, it's your math or high school math. So you are presumed to be familiar with the process of solving a quadratic equation by factoring and by the quadratic formula. So that's quadratic, it's factorable, and you can quickly solve for y or easily solve for y. So in other words, once you substitute x equals 1, you'll be able to get the corresponding y coordinates. And that means there are 2 points in consideration since there are 2 values for y. So the 2 points of tangency are 1, -2, and 1, 3. And we are required to find the tangent lines at those points on the graph. So to be able to do so, we need the slopes of the tangent lines. And as discussed in a previous module, module 1, the slope is simply the derivative. In other words, we will be finding the derivative of y, and this time implicitly. So step 2, find the slopes of the tangent lines. First, find the derivative implicitly. Let me just explain how this was arrived at. So we differentiate term by term. So differentiating x squared, that's 2x with respect to x. Differentiating y squared with respect to x. Chain rule, 2y. Don't forget the y prime. And then here I applied the product rule. I thought of the first term as negative x and y as the second term. So it's negative x times the derivative of y, which is y prime, and then plus y times the derivative of negative x, which is -1, so you have negative y. Anyway, you can verify that. The common error students make in differentiating terms containing negative is in the failure to distribute the negative sign. So actually both have to be negative, but the tendency is to have one of them positive. But anyway, verify this is the correct differentiation. And of course, derivative of the 0 constant there is 0. Okay, we did not just copy the 0, we differentiated the 0, although the derivative of 0, since it's a constant, is also 0. If this were a 1 or a 2 or any other number, it would have been also a 0 here. Now we can solve for y prime the usual way, and just verify that if you collect y prime on one side, factor out, divide, you'll be getting this expression for y prime. Now, once you have the derivative, it would now be easy to get the slope since you have the values of x and y. You have both x and y coordinates. So you just consider one at a time, get the slope. So for example, for the point 1, -2, we just plug in x equals 1 and y equals -2 into the expression here, we get the slope. So I've shown here the substitution and the final value, 4/5. In other words, the slope of the tangent at this point of this curve is 4/5, found by implicit differentiation first. And we do it for the other points, if there are any. So let's do it for 1, 3. We plug in 1 and 3, x equals 1, y equals 3. Simplify, we get 1/5 for the slope of the tangent at this point. Now, that means you have everything you need to get the equation of the tangent lines. They are just lines, so you just need a point and a slope, or the slope. So we use the point slope form to derive the equations. For step 3, we find the equations now of the tangent lines. So let's consider the point 1, -2, whose slope we already know. I mean, the slope of the tangent to the curve at this point. So we just use what we know from algebra. Point slope form, remember, y minus y sub 1 equals m times x minus x sub 1. So y minus -2, so you have a y plus 2. And then here, x minus 1. and then times m. And then we just simplify in the form y equals mx plus p. And we do it for the other point. So we know now that the slope of the tangent there is 1/5 at the point 1, 3. We do the same. And without having to discuss the details, we get this as the equation of the tangent line to the curve at this point. Now, just for the purposes of showing you why our answers are correct, I have used GeoGebra. You can download it on your in your cell phones. I'm not sure how to do it with your computers. And you can type in just the equation of the curve. You can type that directly into GeoGebra, and also the equations of the tangent lines, and you'll see that they are indeed tangent lines to the curve at the given points. So here's the curve, here's the equation. It's an ellipse actually that is rotated, I think 45 degrees counterclockwise. Anyway, that's not important. You won't be required to graph such curves anyway. And here are the tangent lines, the equations we have found. I plotted them, and we see that they are indeed tangent to the curve. And in fact, it's not hard to see that we have the points of tangency there. For instance, this is 1, 3, and this is 1, -2. Okay? And without, of course, showing you the graph, we can still get, I've just shown you that you can still get the equation of the tangent lines algebraically, or rather using the methods of calculus. Is there any question? So let me leave that topic, since all that's needed is practice. Now let's go to derivatives of inverse trigonometric functions. Now, so far what I know is that all you are required is know how to find the derivatives of inverse trigonometric functions and nothing else. In other words, it's just like what you did in the previous module, where you are given the derivatives of trigonometric functions, logarithmic functions, exponential functions, then apply the chain rule. That's all you need here. If you know the formulas, then you just apply them to specific functions given that involve inverse trigonometric functions. And what are inverse trigonometric functions anyway? Of course, from what you know about inverse functions, they undo each other. So these are the type of functions that undo trigonometric functions. So consider the function y equals tangent inverse of x. What does this mean? It's the function that undoes the tangent function. In other words, if y equals tangent inverse of x, then we know that the tangent of y is equal to x. It's just like squaring and the square root. It's just like the logarithm and the exponential. So this equation defines the inverse trigonometric function, or rather this statement. And if tangent y is equal to x, it's also true that y is equal to the tangent inverse of x. However, we only need this in order to derive the derivative of the tangent inverse. And how do we do that? By implicit differentiation. We do not know how to get it directly. So what we will do is differentiate this one instead, since they are equivalent statements. So we differentiate this with respect to x. That means we need implicit differentiation. We differentiate the left-hand side. Okay? And then we differentiate the right-hand side with respect to x. Now, of course, obviously, the right-hand side is just 1. The derivative of x with respect to x is 1. However, for the right-hand side, we need the formula for the derivative of the tangent. And what's the derivative of the tangent? Of course, this is still fresh, secant squared. Times, of course, don't forget, chain rule, the derivative of y. So it's secant squared of y times the derivative of y with respect to x. And the right-hand side, of course, is 1. So that we can solve for the derivative of y. And so it's just 1 over secant squared y, dividing this by secant squared y. However, the derivative is in terms of y. We want it explicitly in terms of x. So we need to solve for secant squared y in terms of x. And it's not hard since we have what we call a Pythagorean identity, which you may not be familiar with. But anyway, in high school, you may have already encountered a Pythagorean identity like this. We don't, this is not actually the scope of the course, but this is under Math 21, though in the previous semester, we haven't included it. But anyway, it's just for you to know that secant squared y equals 1 plus tangent squared y is an identity relating two trigonometric functions here, tangent and secant. So if I want to solve for secant squared y, I just evaluate 1 plus tangent squared y. And based on this one here, what is tangent y? It's x. So what's tangent squared? Squaring, you get x squared. In other words, secant squared y is just 1 plus x squared. And we can replace this one by 1 plus x squared so that our derivative now is exclusively or explicitly in terms of x and x alone, since we need a derivative for tangent inverse x. Now, y is the tangent inverse. So we can rewrite this as follows. The derivative of the tangent inverse of x is 1 all over 1 plus x squared. Now, don't you worry about the derivation. What I've just done here is at least to show you how the derivatives of inverse trigonometric functions can be found using implicit differentiation and the corresponding definition of inverses. So what I'll be doing is just giving you the list or the formulas for the other inverse trigonometric functions. Okay, by the way, sorry. This is the spatial case. Now, what if we have the chain rule, or rather, instead of x, we differentiate tangent inverse of y with respect to x. So we just applied the chain rule. It's the same. So 1 over 1 plus x squared. So therefore, the derivative of tangent inverse y is 1 over 1 plus y squared times the derivative of y. So y prime. Or we can just write it as y prime over 1 plus y squared. And we also do that for the other inverse trigonometric functions. So here we have the sine inverse. Okay. The derivative of sine inverse x, you can just memorize. It's better to memorize, although of course I don't see you, okay, when you answer the quiz or the graded exercises, so you can just write the formulas on an index card. But it's better if you commit the formulas into memory. So it's 1 all over square root of 1 minus x squared. So it's just, it involves a square root and then the expression 1 minus x squared. And if you want the general formula for sine inverse of y, it follows 1 over square root of 1 minus y x squared. So it place x by y, and then times the derivative of y prime. And so with the other inverse trigonometric functions. Cosine inverse, just take note of the difference. It's negative, same but negative. And so with the general formula, chain rule for inverse trigonometric functions. If we just added the y prime and change the x to y. And also the others. Tangent inverse x, what we derive? 1 over 1 plus x squared. This is the general formula, chain rule. And the only difference with cotangent inverse x is the sign. So yung dalawa na lang, secant and cosecant, almost like the sine inverse and cosine inverse functions with the addition of x as a factor in the denominator. Okay? Then y prime added for the general case. For cosecant inverse, just a negative again. Okay, so just commit them to memory, or for now list them down on an index file. Let's just give 2 illustrations on how to use those formulas. 2 are instructive enough, and then practice again makes not only familiarization perfect. Okay, so let's start with a very simple one. Cosine inverse of x squared. Let me write down again the general formula here. Now, suppose you know that already. How do you apply that to get the derivative here? So you just, okay, follow the basic case where you multiply or write down 1 over square root of 1 minus y squared. So in other words, I've replaced y here by x squared. So x squared squared. And then y prime, I just, okay, I've written it here still first, okay? So we differentiate x squared here, and we put x squared here. So all that's left is to differentiate x squared, the y prime. So we have that. Any question? Okay, let's try. Let's have another one. So just follow me for now. Secant inverse of ln of x. So 2 functions are involved. So we need the chain rule here. This is the general formula. What is y? In this formula here, though, we are considering ln x. So if we replace y by ln x, so we have the derivative of ln x on top. Derivative of this one is 1 over x. And then we replace y by ln of y, or rather ln of x. So ln x squared. Then the rest is simplification, although in questions like this, you might not be required to, again, simplify. Kung isi-simplify, ganyan. Medyo gumamit tayo ng spatial notation. Instead of the square being outside, we put it inside to get rid of the need for using parentheses. Any question? So should you have a question, I'm always available for consultation. You just have to schedule an appointment. All questions will be entertained via consultation, not by email. Okay, so if you have any question at all and it has to be explained, then schedule a consultation. So related rates. Okay, this will be the last topic we will be discussing. So related rates. Let's have the example here. Let me read first. A 10-foot ladder is leaning against a wall. If the bottom of the ladder is sliding away from the wall at 3 feet per second, at what rate is the top of the ladder sliding down the wall when the bottom is 8 feet away from the wall? Let me give the figure here. So here's the ladder, 10-foot ladder. Here's the wall, here's the ground, assuming the two are perfectly perpendicular. So we have the figure here. In physics, we call that a free body diagram. Now, to solve the problem, what you first need to do is get or find an equation relating the variables. The variables in this case are the distances of the foot and top of the ladder from the wall and from the ground. So y is the distance of the top from the ground, and x is the distance of the foot from the wall. And using the Pythagorean theorem, you can get the equation x squared plus y squared equals 10 squared. Remember, sum of the squares of the sides equals the square of the hypotenuse. So that's how x and y are related. And once you have that, there's not much of a problem after, since all you need to do is use implicit differentiation. Okay? So since this is a related rates problem, what you need to do is differentiate the equation you've found with respect to time. And time will always be denoted by the variable t. In other words, okay, once you have that relation, you differentiate the equation with respect to t, which is time, both sides. And then you apply the rules, so sum rule, and then since t is different from both x squared and y squared, t now is the independent variable, so you have to apply the chain rule for both x and y. So differentiating x squared, you bring down 2, subtract 1, that's 2x. But since x is now in terms of time, or time now is the independent variable, you add the derivative of x with respect to time. Okay? We are no longer differentiating with respect to x. We are differentiating with respect to time. Both x and y are changing with respect to time. So both need the chain rule, okay, so that we can get properly their derivatives with respect to t. Similarly, differentiating this with respect to t, you get 2y dy dt. And for the right-hand side, we differentiate it with respect to t. It's still a constant function, so the derivative is still 0. And what do we have here? The rates of change. Notice, we have the rates of change of x and of y with respect to time. And this equation now is what we need to solve our problem. If we are looking for one of the rates here, then all we have to do is plug in the values of the other variables. So first, what are we looking for? If we go back a little, we are looking for the rate at which the top of the ladder is sliding down the wall, which is measured by y. In other words, we are looking for the rate of change of y with respect to time. That is what? Dy dt. So going back, we are looking for dy dt. So what we can do now is solve for dy dt, transpose this, then divide by 2y, and then simplify, you get that. So what do we need to get dy dt? We need x, we need y, and we need this rate of change, dx dt. Are we given all directly in the problem? No. What do we know? We are told, okay, if you look back at the problem though, here you are told that of course the ladder does not change in length. It's 10 feet, but you are given this rate of change. The ladder is sliding away from the wall at 3 feet per second. So what is that? The rate of change of x. So that's dx dt. That's 3. What else is given? The 8. 8 feet away from the wall, that's the bottom. So that's x, which I have shown here. So we are given x is 8, and dx dt is 3. But what do we need to get dy dt? We also need y, so we need to solve for y. This is what we don't have yet. So to get y, okay, here you need the Pythagorean relation again. We found this a while ago. So if we know x, we get we can get y. X is 8. So plug in, solve for y. You get y equals 6. And so we can now get dy dt. So now we have three knowns. We know x, we know dx dt, we know y. And we got this a while ago, dy dt equals negative x over y dx dt. So we plug in all those given values. Okay, simplify. We get negative 4. And this is the rate of change of y. So what does this quantity tell us? It tells us that the top of the ladders, because of the negative sign there, is sliding down at the rate of 4 feet per second. Of course, if the bottom is sliding away from the wall, the top should be sliding down. And therefore, we expect a negative result here. Okay. Am I heard clearly? Okay. Malinaw naman, ano? So, sige. There's a follow-up question here. Let me perhaps just finish with this one. Okay. How fast is the angle between the ladder and the ground changing at the same instant? This time, what are we being asked for? We are looking for the rate of change of this angle now. In other words, we are looking for d theta over dt. So we need trigonometry here now. Now, how do you get d theta over dt? You need a relation between theta and the other variables here. And we can either use cosine theta or sine theta. You can use either. But since we are given x directly from the problem, I chose to use cosine theta. And what's the formula for cosine theta? Remember, it's the adjacent over the hypotenuse. Anyway, you can just uh, go over your textbook in Math 21 or search it online for the formulas of the 6 trigonometric functions. It's adjacent over hypotenuse, so it's x over 10. Now, why do we need this? We need to find the rate of change of theta. And if we have this, we can just use implicit differentiation. We differentiate with respect to time though. And with this equation, we can get it as follows. We differentiate the left-hand side with respect to time. We differentiate the right-hand side with respect to time, which I've just written as, sorry, I've made an error. Sorry very much. This should be 1 over 10 x to the negative 1. I made an error. Okay. Let's just go with it. Okay. Just bear in mind that this is supposed to be 0.1 or 1 over 10. So continuing, we differentiate cosine theta with respect to t. We apply the chain rule. The derivative of cosine is negative sine theta. And then we differentiate theta with respect to time. And then we apply the power rule here. We bring down negative 1, subtract 1, and don't forget chain rule also for x. We differentiate the base x with respect to time. And don't forget this is 1 over 10 or 0.1. So that allows us to solve for d theta over dt. Solving, we just bring down negative sine theta over here, cancel out the negative signs. We have this. So that's all that we need to get the rate of change of that angle. We need dx dt, and isn't that already given? But we need one more thing. We need sine theta. If we can get sine theta, then we're done. But with trigonometry, with the definition, we know how to get that. How do you get sine theta? It's the opposite over hypotenuse, right? Opposite is y. This is angle theta. What's opposite? Y over hypotenuse 10. And in the problem, if you still remember, we solved for y a while ago. We got 6 for y. So it's 6 over 10. Let me just use decimals, 0.6. So now we can plug in those to get d theta over dt. So plugging in sine theta, which is 0.6, dx over dt, which is 3, and x, which is 8. Now this should be 0.1. So let me just adjust after. So this is 0.1. So what I got originally was this. So if we do it, okay, we adjust this one. We just move it 1 decimal place to the left, right? 1 decimal place to the left. So it's 0.078125. And remember, whenever we use trigonometry, theta is always in, not degrees, but radians. So the proper unit is radians or radian per second. Okay, the decimal is here, 0.078125 radian. Now, if you're interested, you can convert it to degrees. If you still remember how do you convert to degrees, you just multiply it by this factor 180, then divide by pi. So multiply by 180 and divide by pi, you get, so we move the decimal place also, 4.48 degrees per second at that moment. At the instant, the foot of the ladder is 8 feet away from the wall. The angle here between the ground and the bottom of the ladder is changing at 4.48 degrees per second. However, we will require the use of radians for problems on related rates that involve angular change. Okay. So, is there any question so far? Okay. Okay, I guess it's better to go about this next time. This one actually I borrowed from the module. So if you want, you can study the module first, and then I have another problem actually after this, but we'll reserve it for Tuesday next week since we still have a lot of time anyway. So that's it for today.